All right, welcome to this explainer. Today we're going on a hands-on guided tour of a classic 12th grade physics optics lab. I am honestly so excited to walk you through this because, well, we're essentially going to be measuring the invisible properties of light. We'll be taking these highly abstract concepts, things like focal lengths, real and virtual images, and refractive indices, and we're going to make them completely visible and measurable right here on the lab bench.
So here's our game plan for the lab today. First up, the concave mirror mystery. Second, we'll focus on convex lenses. Third, we'll be measuring the refractive index. And finally, we'll wrap up with the prism deviation experiment. Let's dive in.
Station number 1, the concave mirror mystery. We're going to figure out how to measure focal lengths.
Now you might be wondering, how exactly do you measure a focal length that you can't even physically touch? Well, as you can see, we've got our classic optics bench setup. We have a light source, a crossed arrow target acting as our object, a viewing screen, and our concave mirror mounted on a stand. Our main goal here is to carefully adjust that viewing screen until the image of the arrow snaps into perfect, razor-sharp focus right at its center. What we're trying to do is completely eliminate parallax, when things look like they're in different positions depending on your line of sight.
Okay, so let's break down how this actually works in practice. Step 1, like we just talked about, is placing the mirror and the target onto the bench. Step 2 is fine-tuning that screen to find the absolute best focused image. Then, Step 3 is where the real science happens. This is where we measure and record the object distance, which we label U, and the image distance, which is V. Now, Step 4, absolutely crucial. We don't just do this once, we repeat the process to gather multiple data points. Because, good science requires robustness. We can't just rely on a single lucky calculation. We need a whole series of object and image distances, moving that target closer and further away, just to iron out any margins of error.
So what do we actually do with all those U and V measurements we just took? We graph them. For a concave mirror forming a real image, the formula is 1 over F equals 1 over V plus 1 over U. So we plot a graph with 1 over U on the x-axis and 1 over V on the y-axis. And when we draw our best fit straight line through those data points, something kind of magical happens. Well, actually, scratch that. It's not magic, it's just brilliant geometry. That line is going to intersect both axes. The y-intercept equals 1 over F, and the x-intercept also equals 1 over F. We just take the average of those two values, and boom, we have our highly accurate focal length.
Now, measuring a concave mirror is fairly straightforward because, as you can see on the left, they form real images that you can physically catch on a screen. But convex mirrors? They always form virtual images, and there's no way you're catching a virtual image on a screen. So we have to use a pretty clever workaround. We introduce a convex lens to first form a real image. That real image then acts as a virtual object for our convex mirror. By carefully adjusting the mirror's position until the light rays literally retrace their own path and form an image exactly where the original object is, we can find its radius of curvature, and from that, its focal length. Pretty neat, right?
All right, moving on to Section 2, focus on convex lenses. This time, we are dealing with bending refracted light.
For our convex lens, we're once again going to measure our object distances, the U's, and image distances, the V's. But let's mix it up and look at a completely different kind of graph. Instead of plotting the inverses like we did before, what if we just plot U straight onto the x-axis and V straight onto the y-axis? Look at the shape we get here. We don't get a boring straight line anymore. Instead, we get this beautiful, smooth, distinct curve, known as a rectangular hyperbola.
So how on earth do we extract a focal length from a swooping curve? It's actually based on this gorgeous piece of symmetry. Right on our UV graph, we draw a straight line from the origin at exactly a 45-degree angle. This diagonal line represents literally every single point where U is perfectly equal to V. When we extend that line, it intersects our hyperbola curve at one specific spot. Let's call it point P. According to the rules of optics for convex lenses, when the object distance matches the image distance, that specific distance is exactly twice the focal length, or 2f. So all we got to do is read the coordinates of point P, divide by 2, and we've nailed down our focal length.
Okay, welcome to Station 3, measuring the refractive index using lenses and mirrors.
This is honestly one of my favorite setups. Take a close look here. First, we lay a flat plane mirror flat on our bench. Next, we drop a tiny bit of liquid, let's just say water, right in the center of that mirror. Finally, we place our glass convex lens gently on top of the liquid. The liquid gets squished perfectly into the shape of that gap, which essentially creates a makeshift plano-concave liquid lens sandwiched right between the glass lens and the mirror.
And right above all this, we've got an optical needle clamped to a stand.
Now here's how we actually use this little optical sandwich to find the refractive index. First off, we find the focal length of just the glass lens on its own. We'll call that f1. Then we build our glass and liquid combination. We slide the optical needle up and down until the very tip of the needle perfectly aligns with its own inverted image with zero parallax. That specific height gives us our total combined focal length, capital F. And look at the math here. 1 over f equals 1 over f1 plus 1 over f2, with f2 being the focal length of our new liquid lens. Once we crunch the numbers for f2, we plug it into the lens maker's formula to solve for n, the refractive index of the liquid. It is just a stunningly elegant way to measure exactly how much that specific liquid bends light.
And that brings us to our final stop, Section 4, the prism deviation experiment. Let's talk about angles and dispersion.
So, when a ray of light shoots into a glass prism, it refracts, or bends, 2 separate times, once when it enters and again when it exits. This completely knocks the light off its original path. The angle between the incoming ray and that final outgoing ray is called the angle of deviation. But I want you to think about this. What actually happens to that deviation as we change the angle at which the light hits the prism in the first place? If we make that angle of incidence larger and larger, does the deviation just keep getting bigger right along with it? The answer will probably surprise you. If we trace out the pins, carefully measure all our angles, and plot the data, we don't get a straight line. We get this characteristic U-shaped curve. As the angle of incidence goes up, the angle of deviation actually goes down at first. It keeps dropping until it hits this absolute floor, which we call the angle of minimum deviation, or DM. But if we keep pushing the incident angle past that exact point, the deviation sharply spikes back up. By finding the very bottom of that U-shaped curve on our graph, we capture the minimum deviation. And that is the golden key we need to calculate the precise refractive index of that solid glass prism.
Section 5. Seeing the light. Time for our conclusion. So, through graphing intercepts, finding intersections on UV hyperbolas, building those liquid lenses, and tracking prism deviations, we have successfully mapped out the totally invisible behavior of light. But before we go, I really want to leave you with a thought to reflect on. We just spent this entire explainer moving little metal pins around and staring at blurry shadows on a basic metal table. But ask yourself, how do these incredibly simple 12th grade bench tools serve as the foundational math for massive, multi-billion-dollar space telescopes like James Webb or the entire global fiber optic network that is literally running the internet you're using right now? The answer is that the geometry of light, the exact way it reflects, refracts, and deviates, is completely universal. If you can master the math on a tiny lab bench, you are unlocking the engineering of the entire universe. Thank you so much for joining me on this tour. Keep questioning the world around you, and I really hope you leave today eager to learn more.